Okay, folks. I'm here in our regular space to try to simulate the regular classroom conditions, and provided that the college will let me onto the campus next week, I intend to do the same thing. Right? Alternatively, I figure I would have to try to rig up a board or something at home, which is a little complicated because I live in an apartment and I'm tripping over my sisters as is. Anyhow, here's the agenda. Basically, I'm going to start with making adjustments to the calendar, because we need to. I'm going to spend the majority of time just in this episode, for lack of a better phrase, going over the homework that was from last time, before the break. You had section 6.5 and 6.6. And while I was on vacation, I actually made a handout that I want to at least present to you and direct you to print, because I think it summarizes both of these sections even better. All right, and when we go through the homework, I'll point at it basically. As for the test that is supposed to occur on Thursday, which is technically tomorrow because I'm recording on Wednesday, but for this class, I can't give you obviously a test because we can't meet. I still want you to have the experience just for the sake of, maybe gleaning something useful from it. So I'm going to upload test number 2 into the pages category of our Canvas, and you can print it out and try all those problems. All right? They're all multiple choice, just like last time. All right? What I'll do is I'll basically make it homework. I can't really collect it from you for the same problem because we can't meet. And I would feel bad to say, oh yeah, sit there and try to scan 10 pages or whatever it is. That's kind of assuming that a person has access to, technology that may or may not have it, right, consistently. So basically, what I'd like you to do is, when you can, presumably tomorrow, get me a printer at least, all right? Print out what would have been test number 2 and just work on that as if it was homework, all right? And then when we theoretically meet on Tuesday of next week, we'll just try to go over those problems, all right? I'll see if I can do as many as possible, if not the whole thing, or the most interesting ones. I'm video recording this, and I'm going to upload it to YouTube. Live stream, unfortunately, I can't do from the campus for some reason. I just don't seem to have the authority. Weirdly, I have done it from my apartment, and it's not an issue. I would like to have that sort of interaction, but we're not there yet. All right? So until that actually happens, the best way to communicate is via Canvas in your regular email. Last thing is homework from next week moving forward. All right? I can't do what I had been doing, which is giving you photocopies of the online textbook and circling the individual problems. So what I'm going to do is I'm going to nix that. We'll go over it today, the very last one, 6.5 and 6.6. But I'm probably going to depend a little bit more than I had on my open math. All right? And I'll make those your homework. Right? At least then you could get some kind of a grade as a result of working on the material. Right? Since I can't give you a physical test for right now, it's probably going to lean more that way, right, for the foreseeable future. Right? I'll probably just tell you ahead of time as we progress through the rest of the semester what counts for what, whether an assignment counts for quiz grade or it's just simply to work on for practice. Probably for the most part, it'll be just simply working on the material for practice. Right? I got an email just today that basically swears that if you need to use the computers here on the campus, you will still be able to do that next week. All right? They're very nice, the people over in the IRC building. All right, at least that's where you'll be able to work. The library, no. All right. The IRC building, if you're not familiar, is in between the library and the Johnson Learning Center. All right. Instructional Resources Center. Anyhow, if you walk in between in that middle building, that's the main computer lab. You probably know since it's spring semester. Anyhow, if you need access to a computer, just know that you have that as an option. You can come here, all right, and sit down at a terminal. They'll just they're going to be prepared. They're going to ask you for your student ID, not just any ID, but the Middlesex ID. And they'll space you away from other students just to, for hygienic reasons. Anyhow, let me show you our calendar to remind you where we are, where we're supposed to be, and where we're going. All right, here is the syllabus. Just open and go down to the bottom here. This is a bit much. Back that wolf a little bit, and I'm going to rotate it. Okay. Gotta put my eyes on. All right. We had done sections 6.5 and 6.6 on this Thursday. You might be wondering naturally, well, what's section 6.7? 6.7 is applications of exponential equations. All right, basically it's word problems. For the sake of time, I'm going to nix that. All right, we had gone over some word problem examples with financial, compounded interest example. All right, so that's sufficient for right now. Review day was canceled naturally because we weren't here. Today is Wednesday, and this recording is for tomorrow specifically. All right, as I said, there's no test, all right, that you're going to be given a grade for. All right, it's just going to be homework. All right, then presumably, starting on Tuesday of next week, we'll be back on schedule, section 7.1. All right. Just please, again, do try to print out the test that I'll upload to Pages and Canvas and try the problems, because it's a nice summary of basically Chapter 5 and Chapter 6 material, okay? When I make the final, I make them basically from the tests, right? So it's also good preparation for that, naturally. I'm gonna give you a practice final at the end of the semester anyhow, but, between now and then, do as much as you possibly can, all right, given the conditions that we're here. All right, so this is for today. We're doing sections 6.5 and 6.6 just to review. Let me point to the handout that I mentioned. Let's see. Okay, under Pages, where it says exponential logarithmic functions, I made this new handout, which you see it says in purple no. Try to print this. You'll need, probably as you do the assignments, this handout that you already have, right, at least if you were here before the break, that is a summary of logarithmic properties, right? Also good to have, let me point to this as well, rules of exponents, and I'll open this before I move to the next page. I'll come back to it. An older handout. Let's see. Here we go. That's how I look right now and how I feel. Like Daisy Duck smoking a cigarette and drinking coffee. I don't smoke, but I do drink, I admit. Coffee, that is, nothing else. Don't get funny. Makes me feel more productive anyhow. And I feel like it improves my personality too. I get a little bit more energetic. All right. Anyhow, this handout I'll point to here was the handout that I had given just before the break. All right, on the front page is the logarithmic properties that I had mentioned. I can't show two slides at once, unfortunately, but I had the good sense, thankfully, to print this older handout of rules for exponents, right, which summarizes all that stuff. When you're working with logarithmic equations, very often you're working with exponential equations simultaneously, just they're inverses of one another. So it's good to have this handout nearby. The thing that I have made for today, for the purpose of reviewing the homework, is this. It's a summary of strategies. It's unfortunate, I did make copies, and I was hoping that I would see you on Tuesday and go, yeah, look, this is great, you know, I was proud of this. It's basically a map for how to go about solving equations, all right, which is the usual meat and potatoes of an algebra or pre-calculus class, right? This letter equals this number, or what have you, all right? Well, For those folks who were here for the after period, again, that Thursday before the break, we did do this a little bit. I just drew it as a diagram on the blackboard before they went away for vacation. Anyhow, this is a little bit nicer, a little bit neater, and now you have a copy of it in theory, right? Please try to print this out. Unfortunately, it depends on whether you have a printer or not, but at least have it on hand as you're going through those types of problems, right? It's a good strategy. Let's do this now. I'll try to do basically all of these. Since you're not here to ask me specifically how to do any of them, I'll try to do all of them. One nice thing about having a video is that it could be any length of time and you can skip around in theory. All right, see how this goes. As long as it's visible, let me leave this up for the time being. And we'll go through this. Section 6.5, all right? This handout from the online textbook that we have. All right, for problem 3, it says, for the following exercises, expand each logarithm as much as possible. Rewrite each expression as a sum difference or product of logs, all right? This is not an equation, it's just an expression. So the most that you're going to do, all right, in the case of algebra, is condense it, all right, or simplify it somehow. Expressions, which are basically the building block of equations, all right, usually have this instruction, simplify. All right, simplifying either means, for our purposes now, expand the expression so that is a little bit easier to understand what operations are involved, right? Or condense, right, the expression. Right, which is basically getting it as narrow down to, in theory, the ideal situation would be just one number or just one letter. All right, in which case there's no extra complicated stuff sitting around the expression, all right? These would seem to be contradictory statements, all right? They are opposite of one another, truly, all right? But it is arbitrary, all right, as to say whether something is simplified or not, all right? If it makes something more clear to have something stretched out, it's simplified, all right? If it makes something more clear to have it condensed down to just one number or one letter, it's simplified. Anyhow, that's expressions, right? No equals. You don't see an equal sign, you have an expression, right? Equations, right, have an equal sign, right? And it's usually more the conditioned response of, okay, we're looking to figure out what the variable is. So some letter equals some number. Right? More or less the usual situation, right? Problem 3 is more or less simplifying. So what we're going to need is this slide. Properties of logarithms. Here's problem 3. You're given log of the argument 7x times 2y to the base b. Okay. Now try to make it as visible as possible without obscuring anything else. Here are basically the properties that you have to choose from for the purpose of, in this case, it will be expanding to simplify. Right? If you notice, in the handout, they do have it written this way. There is an obvious dot separating 7x and 2y. If you really wanted to, right, you could start by acknowledging the fact that each of the symbols that are in the argument, the 7, the x, the 2, the y, the letters and the numbers respectively, by virtue of the fact that they are pressed against each other, are understood as being all multiplied together, right? It's kind of arbitrary really to just put the dot there, right? So you could actually do this to expand, right off the bat, all right? Then if you want to, all right, regroup the individual pieces. So for example, if you have log base b here, and I'll just move the parts around, I'll put the numbers up in front, that's considered, if you will, better etiquette, right? Remember, etiquette is how things look, it's not really based upon logic so much as it is aesthetics, all right? The good etiquette of math, if you will, is that we put the coefficients, the numbers namely, up in the front and the letters after it. And since it happens to be x and y, alphabetizing would be ideal too, all right? Anyhow, this is something that exclusively involves multiplication, right? I'll pull this down for just a moment, but in our list of properties, note the product rule, right? It's just two factors in this case, an m and an n for the model, but the result is this, that if you wanted to, you could separate them as a sum, right? It's very similar to the situation that we have with exponents, right? When you have the product rule for exponents, as long as the bases are the same, you would add the actual exponents 3 and 2 and get 5, right? Well, there's some symmetry here, thankfully, right? The product rule for logarithms is when you have multiplied argument factors here, that you could make them a sum as well. So that's exactly what I'm going to do. It's just that I'm going to have 4 things added together rather than 2 things. So you'll get a log of base b, and then the argument in the first part of the sum is just 7. Plus log of base b is 2, and although I'm a little worried about my camera, I'll see if I can get all the way to the board here, but log of base b is x, and then plus log of base b with a y attached to it, right? If for whatever reason you can't see, all right, what I've written past this point is log of x and log of y, both base b's. Plus is separating them, okay? This should be your outcome. Right? It's expanded for the sake of simplicity. Perhaps ironically, it's expanded for the sake of simplicity in that you can see that it is really just a bunch of things added together. Okay. Normally I would ask you, may I erase this? All right? And I'm sorry, I have a bad sense of humor, but I'm kind of pretending that I have a class in front of me right now because it makes me happy to kind of kid around like that. But for my imaginary hallucinated students here, all right, I'll ask politely, may I erase this? Yes, I assume that I can. All right. I haven't completely flipped my wig, mostly because I don't actually have a wig when I really need one. All right. But anyhow, it's always good to be cheerful in times like this, right? Sorry. All right, back to work, Zedwood. Don't quit your day job. All right. Ln. All right, Ln of the argument. Looks like a fraction on the inside. 1 over 4 looks like a superscript k. Just comparing notes to the handout here, and yes, I did duplicate that correctly as well. All right, now again, still going to simplify in the sense that if we can't condense something down to less complexity, then we will expand it to see what all the individual parts are. All right, in this case, let's kind of blend together some established rules. Again, I'm going to turn to my rules of exponents to point at something. You remember that when you have a negative exponent, at least when you start with something like that, that it really is an abbreviation, if you will, for a fraction. So you condition yourself to go, ideally, that, okay, I say a negative exponent, that really means that I make this base number a denominator. And then once I've essentially moved something from top tier to bottom tier, then it becomes a positive exponent. If it's just a regular number in both places, the base and the exponent, then you could simplify it in the context that you could just do the multiplication. All right, and then you'll have whatever fraction there is. We don't have that, unfortunately, because we have a k, all right? But I'm going to kind of write this backwards. Rather than write it in the style of a fraction, which is the way that it's given to me, all right? I'm going to put it like this. The natural log of, if I essentially move this expression back to the top tier, in which case there is no longer a reason for the fraction line, it would be 4 to the negative k. And I could dismiss this. Okay. It is arguably less complicated, i.e. simplified, in this form. It's not finished yet, but it's getting there. Right? Now the next thing to remember is that natural logs are what ln is an abbreviation for. Natural log. Right? They distinctively are a logarithm of base e. So if you want, you can translate natural log ln into what it really represents, which is a logarithm with an e as the base. Right? And the argument is still 4 to the negative k. Now I'm going to go back to my properties and see what I could finagle. My properties of logarithms, which I just erased. Ding dong. So, let's see. Sorry. Yeah, I'm going to open it. Okay. Yes, I'd like to shrink it. All right. Here we are again. If you have, let's see, the power rule, right? Let's start with this. This is simulating log, actually writing the word log with an obvious base that is the e, right? It is simulating the situation that is the power rule, where you have an argument, it's called m in the model, right? And it's 4 in our actual example. And that has an exponent, right? You can write this exponent as basically a coefficient out in front. Which means that this, and I'll move this up just for the moment. Accentuate that. Power rule is now negative k times, I'll make a dot just to make it more obvious, it's a coefficient, of log e to the k, rather 4. Okay. Now if you want, you could leave it like that, and I would be, to me, that's, if it's over-explaining something, it's better, and I would argue that it's more simplified for that reason. However, if you look at the solutions in the back of the textbook in theory, or what are posted online under pages, this being an odd problem, the solution is there. I think they probably put it back into the natural log, in which case it would be this, negative k natural log of 4. It is arguably more simplified, I suppose, because it is slightly more condensed. Right? I like to have something more explicitly stated, but this is probably the way that they have the solution. Okay? Now let's look at 8. Incidentally, if you're worried, especially in light of the situation we are now experiencing, hey, what if you give us, even problems, right? How am I going to be able to verify whether they're correct if you, buddy, are not hanging around at least to, answer a question? I'm going to recommend that you use a certain website. I'll show it to you really quickly. It's called Mathway. There's another one, famously Wolfram Alpha. I try not to talk about these too much, only for the reason that I don't want people to, just automatically gravitate towards the website that spits out the answers, because then, unfortunately, you are circumventing the mental exercise, right? Naturally, we all have calculators and we all have phones and we all have apps, and they're a convenience for us. But as is often the case, the trade-off for convenience is actual experience. And when you're trying to learn something at least genuinely, it robs you, right, unfortunately. So if you want, you could use this website. I like it a lot myself, Mathway, to verify something after you have tried a problem, right? At least you'll know what to look for. In the case of, since your textbook, student edition would ever have all of the solutions. It's usually just the odds or just the even problems, one or the other, right? I would use this just to go, okay, I'm on the right track, right? But don't just go, beep, boop, boop, and get the answer, because then again, what's the point of it, right? Not to digress, but a funny story somebody shared with me recently was that they had purchased an Amazon Alexa, and an Amazon Alexa, will basically answer a person's questions, right? Usually for the purpose of ordering something through Amazon, I assume, right? But it will do the same thing essentially that a Google, iHome or Pod or whatever it is would do, right? Which is, go, hey, you could just randomly ask it something and it will do a search for you. Well, if you're a kid who's in school, doing your history homework, that's probably the easiest thing in the world to have around, right? Oh, what happened in 1492, like if they don't know from a nursery rhyme, they'll go like, oh, it was the age of exploration, Columbus, right? You're kind of circumventing the actual exercise of looking up something, right? You do learn something from it. Anyhow, you may use this, all right? But use it sparingly. I'm sure that I probably didn't have to tell you anyway. Hey, you could go on the internet and look for stuff, but whatever. Right? Just remember that old adage, right? With great power comes great responsibility. Okay. Anyhow, problem number 8 is the same program here. Right? What do we have in this case? For problem 8, maybe I'll put it over here just outside the projection. You have this log base 2 of the argument y to the x. It's similar to the last problem. It is essentially using the power rule once again. If you have something that has an exponent in the argument, you can, according to the power rule, write it alternatively as a coefficient of the logarithm. And now you have that. All right. And that really is as much as anybody can make of it. Okay? Now for the instructions that follow, we're still simplifying, but from the opposite perspective, condensing something, taking something long, ugly, and complicated, and trying to narrow it down to just the bare essentials. So starting with problem 9, I'll pull this down again just to make it a little bit more visible, hopefully. Incidentally, I'm sorry if it might be a little hard to hear me because I don't have an external microphone. And if not that, I also apologize for the chalk, right? I'm hoping that it's visible to a camera. Right? If it isn't, then I'll have to get a whiteboard somewhere. So that's usually a bit nicer anyway. Let's see. If you're condensing problem 9, you have natural log of 7 plus the natural log of x plus the natural log of y. Okay. Start with the obvious. It's a bunch of stuff being added. Right? So although it has 3 parts, this most closely simulates the product rule in reverse. Right? As long as you have all the same type of log, that is, they're all the same bases. Right? In the model, it's just base b for the sake of a letter. But these are all natural logs. Yeah, you can convert them to log with a little e as a subscript if you like, but no sense in doing that. All right? You could leave it like this, acknowledging the fact, all right, I have all the same type of log. and I'm just going to recompile them into one. It is essentially the product rule in reverse. So you would have the natural log of 7xy. A similar problem would be something like number 10. Looks like this. You have the log of base 3, argument 2, plus log of a, base 3, plus the log of 11, base 3, plus the log of b, base 3. Again, as long as they are all the same type of log, that is, they're log base 3, and they are, and you notice that exclusively their sums, right? You can recompile them according to the product rule. That is the product rule, again, essentially in reverse. So, you have log base 3 of the argument 2 times a times 11 times b. All right. I would take the, I would make the added step, or perform the added step of consolidating the numbers at least. So for example, you notice that you have 2 and 11, and since they're just being multiplied, you can make them one coefficient rather than two coefficients. Again, arguably, that's more condensed, therefore it is more simplified. 22, and then you're kind of stuck with AB. This a little less annoying. Okay. 13. You have negative log of the argument in the 7th. Base b again. Okay. Again, this is blending together the rules of exponents, which I'll just flash here. The negative exponent is the abbreviation for a fraction, but if you were to write it backwards, then this would be the result. You have a negative exponent. Now, this is kind of disguised. If you want, they have done some of this already for us. All right, notice that there's a negative on the outside, which means that this is really -1 log of b to the 1/7. I'm jumping the gun a little bit in my mind. Anyhow, let's sort of reverse the power rule. If the power rule, and it's still bearing in mind that negative exponents are an abbreviation for a fraction, but according to the law, the log's power rule, what is a coefficient out in front, and it would technically be -1 if it happens to be a negative at all. All right, it can be written backwards as such. The argument would then have a -1 here. Since they're asking us to condense this, we're going to reverse this process. and basically take this and put it here. And you might wonder naturally, like, well, where do I put the negative 1? Is it inside the parentheses or is it outside? Technically, it would have to be outside in this particular case, which means that you have this thing. 1/7 with a negative sitting here. Right? A person having accomplished that again would go, ah, good, wash their hands of the situation and walk away. But if you look at the solutions available, you'll go, that is a little bit more that you can actually do. Right? And again, I'm going to refer to rules of exponents for that reason. The quotient power rule. When you have some fraction-esque looking argument, the thing written in the parentheses, and it has an obvious exponent on the outside, grouping these two contents. According to the quotient power rule, you can apply the outside exponent to each of the contents on the inside. So what you would end up with is this. Log, the base is still b, with the negative 1 applied to both of these pieces, pardon me. Seven over negative 1. Now again, if you have a negative exponent, it is an instruction to basically move the thing that the negative exponent is applied to its opposite tier. So if in theory it's above the line under normal circumstances, I know we wouldn't write that, but for a regular number, but it would end up moving down to the position of a denominator. That essentially is going to happen twice, but we're going to compensate. This is going to be going down here, and this, because it already is a denominator, would be going up here. So you have this. Log space b of 7 over 1. And once you have actually made that switch, right, the negative becomes a positive as a result of the maneuver. This would be a positive 1 technically here, and this would be a positive 1 technically here, right? It's not making it less complicated by putting the positive 1s in both cases, but it is showing us how this is evolving. So the next thing would be, all right, take out whatever information is now unnecessary. First of all, the positives are optional. Math people, for better or worse, are notoriously lazy. They leave out 1s and 0s and decimal points and positive signs and the indices of square roots. Right. This is really 7 to the first, which means that it is really 7. This is really 1 to the first, which means that it's really 1. And if you want to go as far as you possibly can, the very last step is to dismiss the 1 that is the denominator. So what you end up with as an answer is actually log, and this is still base b, of 7. This is your most concise answer. Here is 15. Is log of the argument x to the 15th, y to the 13th, over z to the 19th. Notice that there's no base number in this case, which means it's a common log. It would be assumed to be 10. Another example, unfortunately, of math people, for better or worse, leaving out information. I would just ignore that for right now, unless you want to put it. It doesn't seem to be needed. Right? Anyhow, it's a common log, so log base 10. In this case, for the sake of comparison to our established set of properties, this most closely resembles what? resembles the quotient rule in this case. If you look in the model, it's just, again, the argument of a capital M sitting on top of a capital N. All right, anyhow, when you have quotients, you can write them as differences, a subtraction problem, essentially. And we'll do that. There is, to add to the mix here, also extra contents above the line, which means that there is simultaneously the product rule going on. Let's start with the quotient rule, all right, and then we'll dissect it a little bit further. And then eventually the power rule as well. First things first. If I apply the quotient rule, this is now the log of the top thing gets written first. So x to the 15, y to the 13, minus the log of z to the 19th. Right. Now at this point, if I narrow my focus to here, and I acknowledge the fact that these are two different letter bases, so I can't consolidate them according to rules of exponents. I can't apply the product rule of exponents and add these. I'll do the next best thing, which is that I could separate them apart. I'll expand them. According to the product rule for logs, this would be the equivalent of log of x to the 15 plus the log of y to the 13. This is still hanging on here, and I'll just, for the sake of clarity, I'll duplicate it here. Never feel bad about writing something incidentally, because what are you doing but showing a person your thoughts? And that's really the best thing that we have. Right? It's a blessing. Right? Anyhow, each of these, we can now apply the power rule. And according to the power rule, if it is convenient for us to do so, we can write this exponent as a coefficient, which means that this is now 15 times the log of x plus 13 times the log of y minus 19 log of z. And that is sufficient. Now, truth be told, there's probably more than one way to do a lot of these problems. Right? 18 is probably a good example of that. Here's what occurred to me. I did it twice actually, and I was much more happy the second time that I did it. Let's see. It starts out as the natural log of these contents. Y beside the square root of y sitting on top of 1 minus 1. That was a weird noise. Okay. Couple of things, right? When you have things pressed together, right, if it makes it more clear, put in the information that's missing, a dot, which means that ultimately the product rule is going to apply here again. And you could do that probably right now if you wanted to. I'm going to do one other tweak first, just because I can't resist it. Sorry. I'm going to fill in the information for the square root. If you feel a little bit sketchy about that, let me point to something from a while back. A while ago, when we had discussed radicals, I gave you this handout. Let's see. No, not this one, sorry. Stare at this for a moment. I'll pull this projector screen down. When you have a radical, as we have in this case, the square root of y sitting on top of 1 minus y, the radical itself, as long as we determine what the index, the type of radical it is, whether it's a square root or cube root or what have you, and whatever the exponent would be on the inside can be alternatively written in rational notation. Now notice that what's different about this from the rules of exponents that had been discussed? The rule of exponent that had been discussed a lot today, all right, was the negative exponent rule, in which case the expression itself, the entire thing becomes a fraction. When you have a radical, basically the radical itself can be abbreviated, the type of radical can be abbreviated as a fraction that is an exponent, right? It's a little bit different. In one instance, the expression entirely is a fraction, and in this instance, the fraction is just the exponent itself. So we need to figure out what is the index and what is the inside exponent that would be written here, n and n. Right? If it's a square root, again, another example of math people being lazy, or arguably, but efficient is a nice way of saying it. If it's a square root, they don't write the index. So I'm going to purposely put the 2 here to make it a little bit easier to adapt it to rational notation. There is simultaneously no exponent written on the inside. So if there isn't anything there, you can make the assumption it's just a 1. Which means that this most explicitly written, that is all of the contents that should be written there are, you would have this, the natural log of y times y sitting on top of 1 minus y to the 1/2. And if you like, you perfectly legally can use brackets instead of parentheses. It's just not to confuse one grouping with another. Right? Parentheses and brackets are usually the same thing when you're just trying to designate what is inside of what. Anyhow, this is really all I've done. I've taken some type of square root. It's an exponent of 2 as the denominator, and converted it to rational notation. Reason being, when I consider my properties of logarithms, I'm not just going to use the power rule, I'm not just going to use the product rule, which is to separate out the y from y sitting on top of 1 minus y, but I'm also going to apply the power rule to the second chunk. So that means that basically the product rule is going to be applied here, and then eventually the power rule. What is happening here is just rewriting more explicitly. What is actually inside this argument. Anyhow, we would have this to begin with, the natural log of y just by itself, and then, because of the product rule of logarithms, a sum, and it would also be a natural log of these contents. Y sitting on top of 1 minus y raised to the exponent of 1/2. And you could probably guess what's just going to happen next. According to the power rule, I could make this coefficient. So this is the natural log of y plus 1/2 times the natural log of, let's see, y sitting on top of 1 minus y. Now simultaneously, the contents of this argument are a quotient, which means that I can in fact go a little bit further with this. When you have an argument that is a quotient, that by itself would be a difference. Just don't forget, both of the things that you write underneath this, right, would in theory have to have this as a coefficient. Right? You could maybe pull a little fast one here. Worry about the coefficient as an afterthought and just sit it on the outside of parentheses. So I'm going to use a bracket in this case. I'm just going to duplicate what's here, natural log of y plus 1/2, and then consider the arguments of this. According to the quotient rule, a quotient that is an obvious top of the line and an obvious bottom, and be rewritten as such. The natural log of the top, written first, minus the natural log of the bottom, 1 minus 1. If you want at this point, just to kind of expose this outside of the bracket to the open air, if you will, apply this, distribute it to each of these contents. Which means the end result would look like this. The natural log of y plus 1/2 the natural log of y, and then minus 1/2 the natural log of 1 minus y. Now it just so happens that if we do that, there's possibly one other thing we could do with the things that are the same type of log, naturals as they all are, but have a similar argument, or have the exact same argument of y. Let me see if the book actually went that far. Yeah, they did. Okay, this is kind of cool. There's no obvious coefficient sitting up in front of us. So this is often the case, all right? If something is not there, what would you assume it is? You can't use 0 because that would make the thing disappear entirely. You can use the number 1, right? You can, at this point, consolidate this sum. These 2/3 of the whole kit and caboodle here. Convert this to something that simulates a situation of like terms. I'll put a little thought balloon up here for the sake of analogy. If this entire thing, instead of it being a natural log and an argument, if it was just one thing, just make it the letter x. No, I don't want to confuse it. The letter u is the u substitution. And it had the argument of, it had the coefficient of 1 sitting up in front of it. It would be 1u. If this thing, which is the exact same log and argument, natural log of y, if I, again, just kind of substituted u, just nothing get distracted, right? This would be 1/2 of u. Under normal circumstances, when you combine like terms, you know the only thing you actually add or subtract of like terms are the coefficients, namely the numbers that are sitting out in front of the letter. So I'm going to add 1 to 1/2. Right? You could use a calculator naturally, but bear in mind, if you have a fraction involved in this, all right, you could write it as 1/2 and then convert it to an improper fraction as an afterthought. Or you could acknowledge the fact that in order to add fractions, I would have to convert the amount of 1 to something that is conveniently using the same denominator. So if the denominator in the second coefficient is 2, right, the amount of 1 whole written in the style of a fraction would be 2/2. 2 2s is 1 whole, right? Anyhow, when you add fractions, normally it's just the top added to the top, and you keep the same denominators. So this would be 2 plus 1, which is 3 sitting over the common denominator of 2, whatever the variable that would be attached to it. And again, I used u substitution here, just not to get distracted. If you want, now put this back, the natural log of y, because that's what u, or whatever letter you chose, actually represents. This is still hanging on here, so I'm going to write it adjacent. And we really, sadly, we can't pull the same trick, because the argument here is something different, right? It's not just the letter y, it's the expression 1 minus y. So you're pretty much stuck with this, right? You might wonder, hey, that kind of looks like one of these properties, but if you compare them to the properties that we have, in no situation do we have a content, the argument of the parentheses in the models here, that start as a difference or start as a sum. The entire logarithmic expression can be written as a difference if you start with a quotient. The entire logarithmic expression can be written as part of a sum if you start with a product. A couple more of these and then we'll do section 6.6. And I'll go over that diagram the new diagram that I made. For condensing is problem 21. The natural log of 6x to the 9th minus the natural log of 3x squared. Notice that the 2 is on the inside of that, attached to the x exclusively. If we were going to condense this, the context of simplifying by making it less expanded, less ugly, and try to narrow it down to just the bare essentials, this problem most closely resembles the quotient rule. It starts out as a difference. So I'm going to consolidate by putting them back in the style of an obvious fraction, top and bottom. As long as they're the same type of log, no issue. It's a natural log, so the contents of the argument here would be 6x to the 9th and 3x squared. And at this point, to consolidate even further, I could remind myself of rules of exponents, which again, I'm going to flash that slide again to remind you. When you have the situation of like base letters, in this case they're x's, sitting on top of each other, you have the quotient rule of your properties or rules of exponents, whichever you prefer to call it. And I know that as long as they are the same letters, I can actually subtract the exponents to consolidate. That means that if I straighten this out, I can deal with the letters, and I can just deal with the coefficients as a normal division. This is the quotient rule of logarithms. This is the quotient rule of exponents. And what I end up with for the argument here, I'll do the numbers first. 6 divided by 3 is just 2. And then if I consolidate the x's, it's 9 minus 2 for the exponents, so it'd just be 7 next to the 7. Right. Now we're back in the situation where if we were going to expand it, we could take advantage of the product rule. I don't think they want that though, they wanted us to condense. So in this case, that's the most condensed way of writing this. As long as it says so in the instructions, I would leave it like that. Condensing is leaving it like that rather than using the product rule. Here is 23. They condense as well. Log of x minus 1/2 the log of y plus 3 log of z, it looks like. Yep. No, that's the Lone Ranger one. Some guy on a horse, you know, not Zorro. Okay. In a minute, I'm gonna just make sure that my camera is still running because I'm always worried the battery is gonna die. But so if I get up and I get over there a little bit closer to you, don't get scared. All right, working left to right. considering what we have, just narrowing our focus on these two. You notice that there's a subtraction symbol here. This is the quotient rule again of logarithms. So to consolidate this, because that's the instruction for this section, condensing, simplifying in the sense that we're making it less stretched out. What we have here is one thing that has a coefficient of 1/2 and one thing that doesn't have a coefficient. I could possibly do this first. I could apply the power rule in reverse. Let's see. Maybe I'll do that first. All right. I want this to look as much alike as possible before I blend them together. If I applied the power rule in reverse, all right, I would end up with this. There's still this hanger on here, 3 log z. I'll have to get to eventually. But I'm basically just moving the coefficient from up in front to an exponent back as it would be. Okay. Now, at this point, apply the quotient rule, which says that I would have log, they're the same type of log, of x sitting on top of y to 1/2. You can, if you want to, convert the fraction that is the exponent, the 1/2, back into radical notation. All right, just to flash this again. If you're starting with something in essentially rational notation, a fraction of 1/2 as the exponent, then it would be written as a square root. Since the denominator of that fraction, and it's an exponent, but the bottom of the exponent is a fraction 2, then you could make that the index. It means it's a square root. And if it's a 1 above, then it would be a 1 on the inside. I'll sweep this in here, and I'll probably have to duplicate it on the other side of the board because I'm running out of space. Log of x still on the top, and then the square root of y underneath. Just for the sake of comparison, I'll exclude it later, but whatever the denominator is, that is the index. That is the type of radical. So it would be a square root. You know that ordinarily square roots, because it's the original concept, it's the OG of roots, I guess you can say. All right, they don't put the 2, all right? Nor would a math person put a 1 here, all right? It would be the most explicit and perhaps the most plain and obvious, but it's considered unnecessary. All right, now I have these things left over. For the sake of clarity, I'm going to duplicate that over on the opposite side of the board. Now I have this. The log of x sitting on top of the square root of y plus 3 log of z. Okay. I'm going to pull that trick from before, which is the power rule in reverse for this term, this chunk here. And it says that this would be written as an exponent here. Now I have therefore the log of x sitting on top of the square root of y plus the log of z cubed. If there's only one content in here, the z, you could dismiss this grouping here, the parentheses. Right? What I'm getting at is that this could alternatively be written like this, and no harm would be done. Okay. Now, they're both the same type of log. They would technically be base 10, which is something you don't have to write. And the obvious operation going on in between these is the sum, which means that this is the product rule expanded. All right, we're going to condense it. We'll put it back, all the pieces together. Means that we'll end up with this. that square root of y will definitely be the bottom. But the contents that are x and z, because z doesn't have a denominator, one would assume that it is a top. And it would be situated next to what also is on top. So x, z cubed. This should be our end result. Good. The last that you had from that section was 25. It says rewrite as an equivalent ratio using, I'm sorry, let me rewrite this. Oh, it's failing. For the following exercises, rewrite each expression as an equivalent ratio of logs using the indicated base. All right, the way that it's written is like so. It's given to you as the log, base 7 of 15 to base e. Okay. And we're going to rewrite this as an equivalent using the specified base, which in this case happens to be base E. All right. To get around this situation, and I'm going to point to properties and discuss the thing that we haven't used very much to this point in the conversation. The change of base formula. Expand this just a bit. The change of base formula is actually a way of getting an older graphing calculator to solve for any type of logarithm. More recently, the software engineers of the Texas Instrument calculator have updated the software so that you could just at will, on the fly, type in whatever type of base log that you like, something other than tens or other than e. So other than the common log and other than the natural log. But if you had an older calculator or the software has not been updated, you actually can use this formula. All right? You would just create this ratio. The n would be a 10 here and a 10 here, the log button on your calculator, or an e here and an e here, all right? E here and e here. That doesn't, I'm sorry, I'm talking funny. E here and E here, all right? Anyhow, having a momentary lapse there. Anyhow, whatever the base is becomes the bottom argument. Whatever the argument is, that is the top argument. Now in this case, what I should probably do is, to make it a little bit easier to compare, I'm going to take the log that they've given us, log 7 of 15, and just write it immediately underneath the model. Log 7 of 15. And then we'll translate it into what the change of base formula would look like. Basically the thing that you would type into your calculator on top divided by whatever you would type into your calculator on the bottom. They're saying it is a base E, all right? In theory, it would be that to start with, log of E, log of E. You probably already know where I'm headed with this, but I'd rather explicitly state what it should be to start with. The top would be 15, and the bottom argument would be the base, which would be 7. Right. Now, to make it a little bit more normal looking, and that is the way that the buttons would appear on your calculator, we would go for the alternative way of writing log of base E, which is to simply use ln. 15 and 7. And this is really what they were after, right? Using the change of base formula if you had to, all right? If you didn't have updated software. Now to prove a point, to prove that the value of this is legitimately equal to this ratio. That this is an equivalent ratio. I'm going to type it on the software that simulates our graphic calculator, and you'll see that you get the same numbers. Pull this down. Okay. Here is a TI-84 Plus, fresh out of the box, presumably. All right, nice software, updated. What you would do. All right. Let's see. Alpha. No, hold on, sorry. Okay, it's alpha window. Okay. There you go. All right. If you hit the button, that is the green button on this type of calculator, or as alpha, that normally is for the purpose of typing letters A through Z. Not that you do that too often, except in maybe matrices. Press alpha, and then press the button along the top that is window. This engages what is function 2 in the calculator. And what you'll notice is that there is a small drop-down menu, again, provided the software has been updated, that has a log-based formula. So option 5 is what you're looking for. All right? Alternatively, all right, if you press the math button, it should be the same thing. I think it's under the menu of numbers, but let me just check. Down towards the bottom. No, apparently it's right off the first menu. Okay. If you press the math button and then scroll down, choice A here is this log base function. Right. In both cases, what this is going to produce is this on your screen, something that says log, and then a void here for where you would type the base number, and then a void here for where you could type the argument. And we'll see what it produces. If the original logarithm was this unique base 7, right, of argument 15, I'll type in 7, scroll over to 15, and you see that it produces this decimal. About 1.39, whatever it is, into infinity. Reserve that, for reference. In theory, if the change of base formula is correct, and it is, all right, you'll see that when you create a situation rigged up like this, that the base is your argument in the denominator, and your argument on top is the numerator, all right, just using ln, all right, you'll get the same value, it's equivalent ratio. Now in this case, if we went with the base E type of log, it's the ln button. If we had, and they didn't ask it in this case, if we wanted base 10, we would just press the log button and it would be assumed that it is base 10. So anyhow, what I'm going to type is ln and then 15 division ln and 7. Okay, and you'll see that you'll get the same number. Natural log of 15, close parentheses, divided by the natural log of 7. And then you have it. 1.39 is the same value. This is an equivalent ratio. Incidentally, this is kind of overkill, but if you feel a little funny about writing something more or less horizontally this way, rather than what is arguably more intuitive, it's stacked in the style of a fraction, there is another function, again, if the calculator has updated software, that you could write it in a more intuitive way. If you go through alpha, and then, I think it is zoom, alpha F1, there you go. Alpha F1, you'll see that it says n/d as a numerator and denominator. Right. Or you can go through the math button and sequence again and choose, I want to say it is the notice menu. You'll have something that shows up on the screen that is a little bit more intuitive. A void where you can enter natural log of 15, and a void down here where you can enter natural log of 7. Use the arrow keys to get around. And then you see the same result. Okay? All right. Let me just make sure my camera is still functioning. So I'm just gonna pull this back a bit here. Yep, looks like it's functioning good. We're an hour and 15 minutes in. And we'll go over section 6.6 now, which is a little bit more satisfying perhaps because it's the equations. Section 6.6 homework from last time. And to get through this, let me discuss the handout that I just made recently. Okay. This again, if you were here for the extra hour before the break, is basically what I was trying to summarize just as people were going away for vacation in theory. You can print this, all right, as long as you go through Canvas. Go to where it says exponential logarithmic functions, and then click on where it says new strategies. What to do when you're solving exponential equations, what to do when you're solving logarithmic equations. And now we have it here. All right. I put this line here to sort of say, okay, anything exponential, that is that you identify up front that you're dealing with this situation, exponential equations. You're going to pay attention exclusively to this side of the divide. Right? If you know up front that you're dealing with a logarithmic equations, and that's the more obvious because it says log, all right? Pay attention to just this side. You can basically, I would say in every case that is possible, as long as you have a graphing calculator, try to graph whatever is given to you. Normally you wouldn't bother doing this, but if you translate 1/2 of the equation into, let's say it's y, you call it y equals whatever that half is, and then draw the second half and call that a second y, right? Wherever the two graphs would overlap, it would be the solution to the equation. Basically the point of intersection. If you don't have a graphing calculator, and this is worth exploring, you could do something, the more traditional algebraic method rather than the graphical method, right? So what to do when you're given same bases, right? Use the one-to-one property. If you have the same bases, whatever number they are, whatever letter they are, right? If they're identical, and just pay attention essentially to the exponents. One could say that the exponents are the only equation that you really need to consider. Right? So whatever is written in superscript here, put it on one side of equals. Whatever is written in superscript here, put that on the opposite side. And then go through it in the methods that we all know, right? Solve by opposite operations. If you're given different bases, right, you can attempt to translate something into a common base and then apply the rules of exponents, which is usually the power rule is really what's involved. Or you can apply logarithms to it. You can apply the common log if somehow there's a 10 involved. Or you could use natural log, which is base E, if there's no 10 involved. If you're given something that is specifically base E, right off the bat, you could apply the natural log and it will induce a cancellation effect. Right? The natural log of E is just the number 1. right? You can test this with your calculator if you don't want to take it for granted. Or you could try factoring. There's probably a problem like that on the test that was test number 2, and I want to say in the homework as well. Something that would be, well, you actually can get away with just factoring it. Let's start with this, and then I'll come back to the logarithmic problems later. Actually, you know what? I'm gonna go drink some water, and I'll be back. Don't leave. Sorry. Get dry, especially with the chalk dust. I'm not wearing it, I'm drinking it and breathing it. Anyhow, focus. Let's start with number 4 from section 6.6. This number 4, you have this problem. I'll put this in a slightly different chalk. Right. 4 minus this weird exponent, negative 3v minus 2, is equal to 4 negative v. Right. Superficially, this might look ugly and complicated, but look at what you have. You have a situation that is this situation. You are given the same basis. They're both 4s. All right? So if they're both 4s, according to the one-to-one property, the only thing that you actually need to zero in on is the exponents. Essentially, what is sitting here and what is sitting here, you can reduce to this equation. Okay? Okay. Now, if you go about this the traditional way, solving algebraically, you want all of your variables on the left. That's usually the case. And anything that is a regular ordinary number on the opposite side. So how do we rearrange the pieces? Opposite operations. I always draw a table like this, you probably know. I'm going to also explicitly fill in missing information. There really is a coefficient of 1 here. So if I want to justify moving, let's say, to make as little work as possible, this negative 3 over to the opposite side, I'm going to do so by performing the opposite of subtracting a 3, which would be namely adding a 3, whatever letter attached to it. And if I do it here, the nice Zen symmetry of algebra is that whatever you do to one side, you are obligated, your hands are tied to do to the opposite side. That makes it legal. So if I'm adding 3 here, for the sake of cancellation, then I must add 3 here. And then I'll combine like terms. They're one of each sign, so I'm going to really subtract them, and I'll get a 2. And then the sign of the outcome will match whatever is the larger magnitude. So since the positive has a larger magnitude, then this is a positive 2. This has a v attached to it. Then I'm going to drag down what is here, negative 2. Okay. Now, last thing is solve for the letter. That is the conditioning, brainwashing that we're all used to. This letter equals this number. I'm going to move the 2 coefficient from here to here. And it is understood, if 2 things are pressed together, they're being multiplied, at least to start with. And if I want to justify moving it, opposite operations. The opposite of multiplying by 2 is dividing by 2. What makes it legal? Consistency. You can get away with murder in math world as long as whatever you do here, do it the opposite side. So divide by 2 here. 2's cancel by design. That leaves you with just the letter V that you're looking for. And then you just have this arithmetic to deal with. The rules for signs, division, multiplication, all right, those set of rules are different from adding and subtracting. One of each sign just simply states that the answer is a negative. And 2 divided by 2 is 1. So your answer is V is equal to negative 1. Okay. Here's 6. Six is 2x plus 1 times 3x is equal to 243. Now, we're still going about our procedures here, acknowledging that we have the same bases, right? At least on this side. So I'm going to try eventually to use the one-to-one property, but as is, 243, it's not obvious that it is actually something that you can produce as a common base of 3. It will work, all right, but if you lack experience, you may not recognize that. Anyhow, let's try, before we start applying rules of algebra, just apply the more fundamental rules of arithmetic, which is to combine together whatever we have on one side, namely the 3's. All right. This is rules of exponents, which again, I'm going to flash this diagram, all right? If I have the same bases, normally I worry about a situation like this when they're letters. The product rule says that if they're being multiplied like bases, 3's in this case, I can add whatever the exponents are. It may not be as nice as a normal number 5, but at least I can consolidate. So basically, these things up here are going to be added according to the product rule for exponents. Okay, so this is going to be 3, I'll put this in a little superscript parentheses here, of 2x plus 1 plus x. And I'll try to blend together whatever I can. This still floating around here is 243. Okay. Now, these are like terms, 2x and, to overstate the case, 1x. We'll consolidate to just 3x. So this is 3 to the 3x plus 1 apparently. Okay. Now at this point I would seem to be quite stuck. All right. I'm going to now go back to my strategies that I had mentioned, and point to a different part here. Right. If you're given different bases, you could attempt to translate into a common base, right? The base on the right side is evidently 3, and the base on the left side is evidently 3. The base on the right side is 243. I'm going to try to go with this strategy, right? Which is to do this, all right? Use the rules of exponents. So if you tinker with this, 243, eventually you can get it into a base 3, right? I would, for the sake of the logic that I'm trying to match bases, start with that it's going to be 3 to something. You could probably get your calculator to do this faster, but if you're trying to talk yourself through the process, I mean, think about it this way. 3 to something, all right? Well, what is the something? 3 to the first is just 3, all right? 3 squared is just 9, because it's 3 times 3. 3 to the third is 27, because it's 3 times 3 times 3. 3 to the fourth, all right, would be apparently 27 times an additional 3. All right, it's probably too short, but we'll see. 21, carry the 2 is 81. All right, this is 81. 3 to the fifth would have to be 81 times another 3. The 81 from the fourth problem, and an extra 3. Perhaps this is it. 3, yeah, that apparently is what it is. 3 to the fifth. So, I'll put this here. We have on one side, 3 to the 3x plus 1 is equal to 3 apparently to the fifth. All right, which means now I can take advantage of one-to-one property. If they're the same bases and they are apparently 3's, I'm going to go ahead and say, according to one-to-one, it's 3x plus 1 is equal to 5 is the actual problem. Moving along. Subtract 5. Subtract now. You know what? Go the other way. I'm sorry. I'll move the 1. So the opposite of adding 1 is subtracting 1 from both sides. This is the cancellation effect by design on this side. 3x is left over. And 5 minus 1 would be 4. And Last thing is to move the 3 coefficients. If it is understood that two things pressed together are being multiplied, then to justify moving it from here to here, I would divide by, this is opposite operations. I get a crummy number, I get a fraction. X is equal to 4/3 apparently. Same as 1.3 repeating, right, or 1 1/3 if you like. But believe it or not, in upper level math, the preference is usually to leave something as a fraction rather than as a decimal. So 4/3 is ideal. That's the answer. Let's do 7. Is this 2 to the negative 3n is equal to, times a quarter apparently, is equal to 2 to the n plus 2. Again, I'm going to gravitate towards these two basic strategies, right? I'm going to try ultimately to use the one-to-one property. If I get a situation where I have different bases somehow, they were on opposite sides last time in this situation, they're on the same side. I'll see what I can get away with. I'm going to try to convert 1/4 into something that is base 2, because this side already is that way. So I'll try to consolidate this is what I'm getting at. If you examine the 1/4, right, start with rigging up a situation like this, right? Let's see if we can convert let's just take the number 4 first of all, and convert it to the same base of 2. What would the exponent have to be in that case just to produce a positive 4 down here? In theory, it would be this. It would be 2 squared. Now, I also would want to ideally convert this to something that's on the same tier, right? Not as a denominator. So what I'm going to essentially do in that case is, and I'll point back to this slide. Remember that a fraction can be abbreviated as a negative exponent. So this, if I grab the whole kit and caboodle and move it to the top tier, we translate this into 2 to the negative 2 times 2 to the negative 3n. And on the opposite side, we still have this n plus 2. Still sticking with one side. Let's consolidate what we can now. Same bases according to the rules of Exponent, the product rule. I would add the exponents. I would add negative 3n plus 2 if it's feasible. I mean, if you can't actually do it, the best you can do is maybe write these things, park them next to each other. Essentially what is happening is that this 2 on the left side of equals will have the expressions condensed down to just one base of 2, and this would be the ugly exponent. Negative 3n plus 2, negative 2. So I'll put minus 2. If you want to write it like this, plus negative 2, no harm done really, but try to make it as least complicated as possible. To say plus a negative is the same thing as saying simply minus. They are technically being added. This opposite side, still n plus 2. Okay, now, thankfully, we've consolidated the left down to a single base of 2. The opposite side already was 2. We can take advantage once again of the one-to-one property, which means that the actual equation that we're going to end up with is this. I hate to obscure this, so I'll put it here. I'll write it above this line. -3n minus 2 equals n plus 2. We have a multi-step algebraic equation at this point. We're just focusing on the exponents that this reduces to according to one-to-one property, and we're gonna rearrange the pieces as always, which is doing via opposite operations. All right, I have a preference. It doesn't have to be this way. I like to put the letters on the left, right, and I put the coefficients and whatever other numbers on the right side. So I'm gonna drag this n over to here, acknowledging that it is really +1, and then perform opposite operation. Opposite of adding 1 would be subtracting 1, and this will amplify. Same signs means that you add, you get a -4n. Simultaneously, just for the sake of space, I'm going to drag this 2 over to here. Via opposite operations, instead of subtracting 2, I will add 2. This already canceled, this now cancels. And I have this, 2 plus 2 is just 4. Last thing is solve for n. Two things that are pressed together, it is implied that they are being multiplied. Move -4 from here to here via division. Divided by n, 4's cancel, become 1, the negatives cancel, become a positive. You just have n, which is what you want. And now you have this, +4 divided by -4, which is -1. Okay, here's 11. We have 9x minus 10 equals 1. Now in this instance, you're not going to be able to translate into a common base, right? No matter what you do, as far as I can tell, right, just thinking about it right now, you'd be hard pressed to translate 1 into a base of 9. Right? Unless you made it 9 to the 0, I suppose. I mean, that would be the equivalent. I'm going to do it a different way in a minute, but it just occurred to me that you can get away with this potentially. So, like bases, I chose 9 to the 0 because as you can see from old distinct rules here, the 0th power rule indicates that virtually anything, the exception is that the base can't be 0 itself, would be the equivalent of 1. So we started with 1, and I just arbitrarily chose 9 because it's convenient. Right? 9 to the 0 would be correct. And that would make me have this. Add 10, add 10, cancellation effect, that should be equal to 10. Let's see, is that correct? Yes, all right, that does work. Let's say, hypothetically, that didn't occur to you to do it that way. Because it's not always obvious that this is an alternative. Let's explore the other option. The other option being, if you are given different bases, you can apply logarithms, right? You can apply the common log, which would be a log of base 10, right? If 10 happens to be involved already, right, would be a good choice, right? Or use the natural log, what would be the base e, right? If 10 is not being used at all, then it really isn't in this case. Right? We already know what the answer is. X equals 10, which is cool, but we'll do it this alternative way because maybe that occurred to you to do it that way. This is often the case in math. There's more than one way to do something, and what you do ultimately, as long as you're getting the correct answer, it doesn't matter, all right? But just realize the power that you have, all right? It's nice to keep in the back of your head, you have options, all right? It's empowering, all right? Here's the same problem, just done differently. if I went this route, and I'm going to go with using a natural log, I would, for the sake of consistency, remember I am fond of saying this and I will repeat it until I die, you can get away with murder in math as long as you're consistent. What makes things legal is being consistent, doing whatever you've done to the top of a fraction, do to the bottom of a fraction. Whatever you've done to the left side of an equation, do to the right side of an equation. If you want to apply a natural log here, right, then make sure that you do the same thing here. A couple of things you could take advantage of, all right? If you have a logarithm, right, and you know that there's an exponent involved here, here's properties of logs again. The power rule says that the exponent can be written as a coefficient. Now I know in the model that's just a regular log, but realize that natural log, ln, is really log with a little e, right? We're just not bothering to write it that way. If you feel more comfortable, right, you could write it like this. Right, if it makes it more clear, I would do that. Anyhow, power rule says I can take this, it's ugly, right, and write it out in front, which means that this is now x minus 10, and log of base e is really natural log. It's a 9. And this log of base e is really the natural log of 1. Okay. Now, move, we've gotten basically the variable that we've been searching for on the normal sort of tier. So what I want to do is move things away from it. I know that this is a coefficient that's ugly. It's a letter minus a number, but think of it as just one thing sitting up in the front. If you had a situation like this, where you had, I don't know, 8 with an x attached to it, and there was, I don't know, 16 on the opposite side, you wouldn't think twice. You'd go, oh, I'm going to divide by 8 to move that, right? What we're going to do instead is pretend that the thing that we have here, x minus 10, is not the coefficient so much as it's the variable, right? And that this natural log of 9, which would be a decimal number, that's the coefficient, right? Move this rather than this. They're being pressed together, so therefore they're being multiplied. And to justify moving something is to perform the opposite operation. So I'm going to consistently divide by the natural log of 9 here, and there'll be a cancellation effect because it's some quantity, whatever it is, divided by itself. And then to make it legal, if I did it here, I'm obligated to do it there. Natural log of 9. Okay. Anyhow, what do we end up with? We have x minus 10 is equal to this. Natural log of 1, sitting on top of the natural log of 9. It just so happens that if you took the natural log of 1, and it might be a little bit more obvious in this case, if you typed this into your calculator, this by itself is 0, which means that whatever decimal that the natural log of 9 is, it would be divided into 0, which is perfectly legal. You could do that, right? You can't divide by 0, but you can divide into it fine, all right? What is 0 divided by anything, though? It's just 0. Which means that you have a 0 here, which brings us back to square 1, right? The situation from before. The faster way, admittedly, of doing this, all right? And you would just move 10. There's more than one way to do it. I know it might seem silly to go, why did I go through all that rigmarole for? Because it's a mental exercise and it's the experience ultimately that's valuable. The answer to the unique problem is less valuable ultimately than the experience that you have. Anyhow, when you have a situation where you can't pull that trick, right? Now you've seen that it works, because you already knew what the answer was, that x is 10. is 17. I think I might get a sip of water again in a minute. Don't mind me. Okay. In this case, you're starting out as base e to the negative 3k plus 6 is equal to 44. All right. So, you are involving an e here. Let me just flash the slide for strategy again. We have this situation. We've done things this way a lot. We've done things this way. And we've now tried doing things by applying a natural log to both sides. Now, when you have a situation where there is a base e to begin with, ultimately you probably would like to apply natural log because there'll be a natural cancellation effect. But we may need to do a little tinkering first, right? Moving stuff around in more or less the usual way. So, making my tables like I like I do, all right? Move 6 from here to here. The opposite of adding 6 to justify moving it would be to subtract 6 both sides. That balances it and makes it legally correct. There will be intentionally a cancellation effect here. This is the junk that is left over. E to the negative 3k equals the outcome of 44 minus 6, which is what, 38? Okay. And now I can take my, well, I can probably apply the power rule. Let's see. Yeah, okay. If I would take the natural log of this, now, the natural log of e to negative 3k, no harm in that, but just make sure that you're consistent. You get away with murder as long as you're consistent. Whatever you do to the left, to the right, natural log here, and I'm going with natural log because I know it's going to cancel e at some point. The power rule says that if you have an exponent here, you could write that as a coefficient, which means that this is negative 3k out in the front. Natural log of e is equal to this natural log of 38. Okay. It just so happens that the natural log of e, and I purposely wrote it on here, is 1. Right? If you were curious as to why, remember a natural log abbreviated as ln is really a logarithm of base e. If you have the situation where the argument happens to coincidentally be e, then you have this situation, all right? I know that this is not an equation unto itself, but remember when you're converting from exponential style of writing these problems to logarithmic style, which is what it is, that you can simulate sort of a teeny tiny little equation in and of itself, all right? If you wrote this rather than a logarithmic style but exponential style, draw the little jelly bean. Remember, this is the base always. Whatever number you have here, let's just make it y, not to confuse it with the letter we're looking for, would look like this. And you would read it sort of like this. E to the y is e. Well, what situation would cause that? It would have to be 1. Right? So if you have the natural log of e, it's 1. Right? Anyhow, if this, in its cancellation effect, really just produces the amount of 1, and it's 1 times the coefficient that we wrote out in front of negative 3k, which means that it's negative 3k is equal to the natural log of 38. Then you're just going, since you're solving for the letter, divide by negative 3 here, there's a cancellation effect, and be consistent. Your answer should be this. A natural log of 38, whatever it is, sitting on top of negative 3. It would be a decimal number, so probably leave it like that. this thing just before I want to get a sip of water, if you don't mind. You have something, 21, in this section, it looks like this. E to the 2x minus e to the x minus 132 is equal to 0. This is an example, and I'm almost certain that on the actual test number 2, I had a similar question, as my recollection serves me. Anyhow, it has base e's in it, and you may want to go this route, which is to apply the natural log. The difficulty with that, unfortunately, in this case, is that you would have to move e's to the opposite side if you wanted some kind of simultaneous cancellation effect. What you have here, and it would be a better strategy, would be to maybe use u substitution so you don't get distracted, right, with fine details, the minutia of 2x and x, and try to factor this. The reason that I would try to factor this in more or less the usual situation, because it kind of simulates a quadratic equation. And you may or may not remember, quadratic equations, the most basic method, I'll flash this old slide to point to it, is to factor and then use the zero product rule. Here we go. When you have something that is in this basic shape, where there's an obvious 0 on one side, or if you can manipulate it so that it looks that way, that it is 3 terms, and the lead term is something being squared, as it basically is in this case, and that the middle term is half that amount, which is 1x in this case, then maybe we can get away with factoring it, right? And if you're going to factor it, then you can take advantage of the zero product rule, which is to write 2 smaller sub-equations, if you will. Right? Maybe natural log will appear at that point. Anyhow, we have this shape, a trinomial-esque looking thing, right, already set equal to 0. So, if you want, just not to get confused, leave it alone. Here. When you have a trinomial, normally what do you expect? A trinomial is something that has 3 terms, right? Separated by pluses or minuses. It usually factors into a situation like this. A binomial, plus or minus some 2 parts, sitting next to a second binomial, some plus or minus 2 parts. Right? If we want this to basically factor out nicely, let's figure out first what should be sitting in the front of each of these parentheses. Normally it's the situation where it is simply x squared, right? In which case it would be x times x, right? An x in the front and x in the front, all right? What we have instead is we have the letter e instead of the letter x. And we have the actual letter x up in the exponent, right? What is actually going to work out in this case is that it's going to be an x here and an x here. So e to the x times e to the x. If you multiplied these things as if you were foiling it, right? This should be the result. 2x. How come? Because if you multiply like bases, according to the product rule of exponents, you would add the exponents. And if it's 1x and 1x, what's 1 plus 1? 2x. Right? So far, so good, right? Here's proof of that again. When you have like bases, they normally are just the letter x, not an e, granted. You would add the exponents. 3 and 2 would be 5, right? Well, if they're just e to the x and e to the x, x plus x consolidated is 2x. All right. Now, then there's the number in the back here, 132. Normally, the number 132 is outside the realm of familiar, right? If you did my multiplication handout that I had for extra credit, one of the things that you were to rewrite over and over again for that old exercise was 11 times 12, right? And what's 11 times 12? If you have it memorized, you would recognize, right? That's something that I can use potentially here and here. 11 and 12. How come? Because simultaneously they're being multiplied to produce this number and subtracted to produce this number, right? 11 and 12 would be the best choice because 12 minus 11 at least is 1, right? If you want it to be a negative, you would attach a negative to the 12, and if you want to cause subtraction, you would have one of each type of sign. So you would have this basically. Just to be square with you, I only put this here for the sake of analogy, because you have to actually use e's because that's what the problem actually is. But if you just saw x's, you probably wouldn't be scared too much. If you saw this problem, x squared minus x minus 132, right? You probably can get to this point, lickety-split, and not have any issues. Right? Just realize that you're just using a base e instead of a letter x. This is all still equal to 0, right? Now, according to the zero property rule, which is subscribing a label to something that you already take for granted, perhaps this quantity by itself is equal to 0. And if it is, then whatever this is, regardless, would be 0 times that mysterious quantity would still produce 0. Either this is 0, and that isn't, and you get 0 as the outcome, or this is 0 and that isn't, and that's still the outcome, or both of them. 0 times 0 is still 0. So what the bottom line is, I'm going to split this active incarnation of the problem in half and write two smaller sub-equations, if you will, both set equal to 0 each. In other words, say to yourself, either the x plus 11 is equal to 0, and we'll solve that. And then this one, either the x minus 12 is equal to 0. Now, if you rearrange this one, just like when you rearrange this one, you move the number from here to here. You'll do it via opposite operations. In this case, it would entail doing subtraction instead. You get a negative 11 on that side. Running out of space, so I'm going to write what I'm doing over here. E to the x is equal to, after this cancellation effect here, negative 11. And then on the other side, moving 12, after the cancellation effect, would produce e to the x equals positive 12. Now let me warn you of something. When you have a natural log, pardon me, when you have a base e, okay, and the outcome here is negative, be suspicious. Right? When you have a negative outcome. What it means is that this is not defined. I'm going to graph the e function, all right, and you'll see that you never have a negative value for y. All right? So if you see a negative value on the opposite side, and really what this is this if you were going to graph it, right? It always would have to be a positive according to the picture. So what's probably going to happen is that you're going to get some kind of issue here, right? Not your fault, it's just extraneous. of that phrase. Extraneous solutions usually arise from squaring, or multiplying or dividing by a variable. Right? But they can arise this way as well. Right? An extraneous solution is basically a dud, all right? A bad solution, something that does not work when you actually check it. Okay. Let's see. Let me show you how it looks as a graph. So you'll see what I'm getting at here. If I'm pretending for a second that this is y equals, and that's the unique function. It's usually written like this, oriented like so. This is just equivalent. And I attempted to graph this. What you'll see is that you get the quintessential E function picture, which is a curve, right, that goes through the point 0, 1. Anyhow, if you wanted to basically get your calculator to graph this, for the sake of clarity, and having to do it by hand, you can get it to type E by engaging second, the blue button, and then you'll notice behind the division symbol, let's see if that's the best choice to do that. Oh, pardon me, behind the natural log, down here, it'll spit out e to the x. And I'll just put the variable here by pressing x tau theta n, it's automatically x. Okay, now let's look at how it graphs. This is a famous graph. The E function graph, if you were to go just behind the y-axis, all right, you see that part of the graph exists back here, but one thing that should be noticeable is that the y values, even if the x values are negative, the y values are never negative. Is to zoom in slightly. Zoom in 2. It famously, like most popular functions, goes through some quintessential point. In this case, it's the location of 0, 1. Right? There are negative x values this way. But no matter what, there's this asymptote here. Right? Bottom line is that, and that's the x-axis, which is y equals 0 by another name. Your y values are never going to be negative. And since this number, negative 11, in theory is sitting in the position of y, again, be suspicious. It's going to be extraneous. There's no solution for that particular factor. Right? The only solution that you're going to get bottom line is for 12. Right? Anyhow, how would we do that? Take the natural log of e to the x, and then again be consistent. The natural log of 12, right? The power rule says that you can put this out in front, in which case this is natural log of e times x, and this is just whatever decimal it is. The natural log of e is a cancellation effect, because it is a log of base e. You know, a situation that would produce that would be if this was 1. 1 times x is just x is equal to the natural log of 12. Whatever this decimal is, that's the answer. If you did the same situation here, just to show some symmetry here, let's say you didn't notice that this was a negative. All right, natural log of e to the x, natural log of negative 11, right? When you got this far, and you typed natural log of negative 11 into your calculator to see whatever decimal it is, you would get in trouble, right? This is going to, again, natural log of e is just going to be x times 1 because of this. And it's just x would be equal to this, negative 11. This is going to produce an error, right? Why? Because it's an extraneous. The y value, all right, can which is the argument here, is negative 11. That's the y, technically speaking, can never be negative, all right? These types of graphs, unless there's some kind of extra transformation, all right, are negative, are never negative. Here is the actual outcome as a decimal. All right, if you took the natural log of 12, you'll see whatever decimal it is. You would press this button, 12, and see what you get, 2.5 almost. Right. Whereas if you typed negative anything, and do be careful, when you are trying to enter a negative in the argument, use this button rather than the minus. You'll see you get an error, right? Because it's undefined, right? There are no negative y values. Yeah. Natural log of 12 is the more concise way of writing the answer and also represents all of infinity. So this is the preferred way of writing it rather than the decimal 2.48, whatever it is. I'm going to get a sip of water, I'll be right back. Not turning off my camera. Nope. Piscataway punch, as a beloved chemistry professor once called it. Okay. It's true. A lot of minerals in that water there.
Not necessarily good ones.
Okay. All right, let's see. Let me check my camera, make sure it's still running. Battery hasn't died. Yep, looks like it's going good. Sorry to give you nausea there by moving you. Back to our strategies here.
My email, what am I doing? Sorry, I shouldn't be showing my email, but hey, whatever.
There you go. Okay. Here we are again. We've done a lot of these problems, all of these type. Anything that starts as exponential, right? Probably we're going to get into now are things that start at least as a logarithm somehow. Okay. Yes. Okay. So for 29, you have this to begin with. The log of 1 over 100 is equal to -2. Let's see what this most closely resembles as far as our strategy is concerned. Yes, you can pull a similar trick, and I think the last question in this section actually asks you to do it that way. So I'll come back to that. You can graph and look for the point of intersection in your graph. Right? That would be the answer. If you're given the same type of log, that is you'd have a log on both sides, then it's the one-to-one property. Right? But if you have a situation where you have a log, this is more or less the normal case, where you just have a log of some argument, whatever the argument is, equals something on the opposite side, a number usually. All right, attempt to translate into exponential equations. All right, apply the properties of logarithms. The inverse property is something that is handy. In this case, let me start with this. We could take this and translate it via rules of exponents, negative exponents, into something that looks more like this. It's 10. Oh, let me start with this. Let me try to translate the number down here into something convenient. 100, all right, is famously written as the exponent 10 to the 2. If I want to go one step further, I could, via the negative exponent property rule, whatever you want to call it, switch the position of 10 squared from down as a denominator to on the normal level. So it would be 10 negative 2. Right? If you want, since there's no other content of this parentheses, you could put it on the outside, it doesn't matter. Right? Meaning, to write it like this is perfectly fine. Anyhow, according to the power rule would suggest that you can put this out in front as an exponent. Right? There is something else going on here, though. I haven't even touched the other side yet. What's going on here is that even if I went from negative exponents, let's see, to the power rule here. All right, I've gotten this far. This is still a log with no apparent base written there. Right? It just so happens that when you have no base written there, that you would assume it is which? E, or is it 10? It's a common log rather than a natural log. Common log is base 10. Which means that if you want to be a little bit more explicit and fill in the missing information for the sake of clarity, what you actually have here is this. Meanwhile, the other side is still negative 2, negative 2, negative 2, negative 2. I haven't even touched that yet. Anyhow, let's look at properties of logarithms for reference. Which does this most closely resemble? When you have the situation where the base number and the argument happen to be the same number, whatever they are, they happen to be 10s in this case, it is equivalent to just 1. There is essentially a cancellation effect. Again, if you converted this from logarithmic style to exponential style, you would see, you'd read it this way: b to the first is whatever the argument is here, b, right? And the only situation that would make that true would be that the exponent would have to be 1. Okay. Anyhow, the bottom line is that this expression, like base, the base and the argument are both the same number. They coincidentally happen to be 10. This is really just 1. It is, for all intents and purposes, a cancellation effect. And this is the result. Negative 2 equals negative 2. Right. The instructions I should have just read before I jump the gun here are asking you to basically prove that. All right. Consolidate one side to show that the opposite side is correct. Right. The instructions officially for 29 were the following. Use the definition of a logarithm to rewrite the equation as an exponential equation. If I had done it the way that they really wanted to, it would look like this. I'm sorry, I jumped the gun a little bit here. If they had done it according to the instruction, which is rewrite it, rewrite the left side, rewrite in exponential form, then what I should have done is acknowledge that there was a common log right off the bat. And if it is base 10, again, pull the jelly bean here, 10 to the negative 2 is, we read it counterclockwise, 1 over 100, right? This is proving that the left side is in fact equal to the right side. Okay. Let's see. Making translated this, it would be 110 squared, and again, if you translated that a little bit further, it would be 10 to the negative 2. It is what it is. All right, 33 forward is the more or less the usual situation. We're looking for whatever the letter is equal to whatever the number turns out to be. This letter equals this number. I'm trying to prove something like this. I'm skipping 31. I'm sorry. In this case, they want you to use definition of a logarithm to solve the equation. All right, fine. Here we go. You have this. You have 5 log base 7 of n is equal to 10. If this were just the problem 5 times x or u or whatever you like, how would you go about doing that? You would move the 5 right off the bat. Right? So I'm gonna still doing that. As long as I have a coefficient here, it would be in my best interest to kind of narrow it down to just log expression on one side. Right, so I'm going to move this 5 over to the opposite side. How do I do that? Opposite of multiplying is dividing. Divide by 5 here, and I end up with this. The log of n base 7 is the outcome of 10 divided by 5 is coincidentally 2 again. And now I can take advantage of converting this. I can convert from log style to exponential style, if you will, notation. How so? The jelly bean, if this is the base, it is always the base. This becomes the exponent, what the thing is equal to. And then you read it like this. You read it counterclockwise. 7 squared is equal to n, right? Then do the arithmetic. 7 squared is just 49. So n would have to be 49. Here's 33 finally. Let's see. And then just the instruction is simply to solve. Okay. So you have 4 plus log base 2 of 9k is the variable in this case, is equal to 2. Whoever the author of the book is, they like the number 2. I guess it works the easiest. Again, try to narrow it down to the situation where you just have the log expression on one side. So before we move the coefficient of 5, now I'm going to move the added number 4. It is understood that if there is no sign here, that it is a positive. And if you want to justify moving 4 from here to the opposite side of equals, you would subtract in both cases. There's a cancellation effect. What's left over here is log 2 of the argument 9k is equal to positive 2 and minus 4. One of each sign dictates that you actually do subtraction. That produces the digit of 2, and the sign of the answer will match the larger magnitude number. So if the larger magnitude is a negative, this is a negative. Okay. Now I'm going to pull that other trick, which is to convert from logarithmic notation to exponential notation. Style notation, whatever you like. Jelly bean, the base is always a base. This is what is the exponent, is -2 apparently. And then you would read it counterclockwise, is whatever's the argument here, 9k. I know it's awkward to have the letter on the right side, but that's just the way it works out in these types of problems. If you have 2 squared, it would just be 4, but bear in mind that this is 2 negative 2. So what does that mean? It means that this is really a fraction. Okay. So this is really 1 over 2 squared, this is the negative here. And that means that this is really 1/4 is equal to 9k. Right? The last thing is that you're going to have to combine the 9 with the 1/4. I'm running out of space, and it does have some minutiae, some fine details to it, so I'm going to rewrite that over there. If in the sort of normal orientation, we have the variable on the left, doesn't have to be, but I kind of like it that way, and it equals 1/4, right? We would solve by moving the 9, right? And it's understood again, two things pressed together are multiplied, so if you want to justify moving it, you would do opposite operations. The opposite of multiplying is dividing. The 9 would cancel by design over here, and then you would do the same thing here. It isn't wrong if you wrote it like this, right? But bear in mind, especially if you don't have a calculator, that this is a division of fractions type of problem. So an old rule from arithmetic is going to rear its ugly head, perhaps you could say. What is going on here is really this. 1/4 divided by 9, if you wrote it more horizontally rather than vertically, or stacked, you might say. Anyhow, k would be the outcome of 1/4 divided by 9. Sure, you could just simply type this into your calculator and it would spit out the answer, right? But it probably is going to be automatically the decimal equivalents rather than the fraction, which is the way the answers are. Sorry, I choked us. The answers are presented in the style of a fraction. I'm setting a bad example. I'm sorry, I should have sneezed into my elbow. Thankfully, no one is here. All right, my imaginary class here will not be infected. All right. I'm not making light of it, honestly, but my instinct was, should have been this. Anyhow, when you divide fractions, somehow, all right, remember, keep, change, flip. Which means keep the first fraction as you see it, change the operation to multiplication, and then you flip the second number. It's always the number on the right side of this symbol. Since it isn't in the style of a fraction to begin with, just remember that you can make anything look like a fraction by sticking a 1 under it. We multiply by its reciprocal, that is the number flipped upside down. So if it's 9 over 1, technically it would be 1 over 9. And that means that k is top times top, bottom times bottom, 1/36. So far, we have basically been doing this. Given a situation where we have a logarithm equals some number, attempting to translate into exponential equations. That's the conversion of when you draw that sort of jelly bean shape around the base and around the number on the right side. It's making it exponential. Let's see. If you have a situation like this, 36, let's see. The natural log of 10 minus 3x is equal to negative 4x. All right. We're going to gravitate towards this. When you're given the same type of log, all right, on opposite sides of equals, all right, you could take advantage of the one-to-one property, which is basically zeroing in on the arguments only. This is a natural log, this is a natural log. So the reduced equation would just simply be paying attention to the arguments here and here. 10 minus 3x is equal to negative 4x. Then you would drag the letters over to one side and the numbers over to the opposite side. To justify moving negative 3x, add 3x, add 3x. 10 is left over, is equal to a negative 4 plus 3, one of each sign dictates that you actually subtract, which means the number will reduce to 1, and it will have the sign of a negative. If you want to justify moving negative 1 from where it is, divide by negative 1. X would be equal to positive divided by a negative is a negative 10. Was the next one. The natural log of negative 3x is equal to the natural log of x squared minus 6x. Right. Again, this is an example of using one-to-one because they're both natural logs and nothing but natural logs on each side of equals. So we could just zero in on the guts here. Negative 3x is equal to x squared minus 16x. Now what's probably going to happen in this case is that since the degree of the expression on the right side is 2, it's going to end up being a quadratic equation. Or something like it. I'm going to drag this 3x from here over to blend it together with negative 6. It's like term. So opposite of subtracting is adding. I'm going to park it underneath the thing it most closely resembles. I don't know what x is yet, but by sheer logic alone, something minus itself cancels out of existence. Normally I wouldn't bother writing a number here, but I'll fill the void with 0. X squared is left over. One of each dictates I subtract. You would get a negative because of the larger magnitude negative. And you get negative 3x. Now, this isn't going to be too complicated, but we're going to go back to factoring techniques because this is one of our methods for solving a quadratic. Right? It isn't as complicated as a trinomial set equal to 0, but I could still factor it certainly. And if I could factor it, then potentially the zero product rule would be useful. If you're attempting to, boring myself is what I'm doing. All right. If you're attempting to factor or binomial here, start with the more basic technique. I think I had given you this handout for a while, from a while back. Let me just point to it. Different methods of factoring. There's several. As a rule, or a rule of thumb, what I would encourage you to do when you're factoring is, if you had a trinomial, you could probably just try to reason it through, all right? An alternative method would be AC product pairs and factoring by grouping, all right? That isn't needed in this case. I would, as a good rule of thumb, try to start with the least complicated method of factoring, all right? Especially if you have something that's pretty narrow, you know, it's just a binomial. Try to look for something similar in each term, in this case it's a letter, and write that outside of a parentheses. Kind of rip that out of each of the terms. So you'll see that in this case, they have an obvious letter X in common. So if I were attempting to factor this by the GCF method, it would be something sitting outside of parentheses, the thing that is in common, and then some reduced guts left over on the inside of parentheses. If x is what is in common, and it would be no greater than x to the first, a smaller one ironically, all right, then we'll see what this shrinks to. X times what would be x squared? X. X times what would be negative 3x. This minus 3, because the x is already accounted for. That's completely factored. And it's already set equal to 0, so therefore I can use the zero product rule, right, to figure out what the letters actually are. So this x is one factor, and it has nothing to negotiate, nothing to move around, navigate. So that's one possibility. X could be equal to 0 in one half of this. If you had this one, and we assume that this is equal to 0, we would just have to manipulate the 3 by adding. So that means that the other solution is this. X is positive 3. Two answers for this, because it was quadratic. It turns out, even though that this is correct, is that they actually are both extraneous, which is not anyone's fault. If you get an answer and you've done perfect arithmetic and perfect algebra, and you've applied all your properties, right, and you still get a dud of an answer, not your fault. All right. A good habit is to check your answer in the original solution, right, and just make sure that everything is legit. For example, one might be a little bit more obvious at this point. If I took this positive 3 and inserted it in here where x is supposedly the value of positive 3, what is a positive times a negative? Coincidentally, it's the same digit of 3. A negative overall. All right. Let's see what you get if you had a log of a negative number. Let's see. Natural log of negative 9 gives you an error message, right? Because the argument is the value of y, right? What is sitting in the contents of the parentheses would technically be the y value, right? And if this was graphed, all right, you're not allowed to have negatives for a y value for a log, natural log, because it's undefined, right? So that would be a dud, right? If you attempt to use 0 in this case, natural log of 0, I don't believe that will give you any trouble, all right? Well, it would actually, because that's the asymptote, and y equals 0 would be in fact the asymptote. So here's proof. Natural log of 0, clear. Should be undefined as well, right? If it was just a hint bigger than 0, 0.1, you know, or something in between those, all right, it would be fine, as long as it's positive. If it's 0, that represents the asymptote, that is the imaginary boundary that the curve will not go through. If this is what the log graph looks like, it's going to approach the x-axis, which is y equal to 0, but it will never actually touch it into infinity. Right? So it's undefined along that line. This is another example of an asymptote, an imaginary boundary. So both solutions, even though the arithmetic and the algebra work out, extraneous. Not your fault, just happens. One other problem gives you a situation like that, but not as bad as it is in both of them. Specifically 45. The 45. Hopefully you can see this. This is 45. Natural log of 7x is on the end of this. All right. what you might do is attempt to pull the one-to-one property since we can't really use this situation because we have logs definitely on both sides. Right? They're both natural logs granted, but even if we manage to consolidate this, and that's really what we're going to do, we're going to get kind of stuck with this situation. Right? We'll just examine, this is ideal anyway, the arguments. Anyhow, we need to use properties of logarithms to condense this, to consolidate. Right? Which again, just to remind you, is this. Yes, we'll use one-to-one property eventually, but bear in mind, they start out as a sum. So therefore, the product rule would be the appropriate property to use. All right, and we'll consolidate this into just the natural log of x times x minus 3. And if you want, you could put brackets here instead, make it a little bit more distinct here. Natural log of 7x. All right. And now we have the situation, although it is ugly, we've gotten it down to just one logarithm here on the left side of equals and just one logarithmic expression here, which is now one-to-one property. We just pay attention to the contents. So if it is x times x minus 3 is equal to 7x, we'll tidy up the left side, distribute x, would be x squared minus 3x is equal to 7x. Scoot 7x over here, understanding that this is really a positive, so to justify moving it, we subtract, and combined it with its like term, which is 3x. Again, normally wouldn't bother, but in this case, fill the void left behind with 0, because then we can apply the zero product rule more obviously. These are the same signs, so this causes addition as opposed to causing subtraction. One of each causes subtraction. Both the same, as in this case, causes adding. They amplify rather than shrink. 3 and 7 added is 10, and it will be negative regardless, so there you have this. X squared minus 10x is equal to 0. I would attempt to factor again. Most basic form of factoring is the GCF method, which is again identifying what is in common and writing it on the outside of parentheses. This again is the situation where they evidently have the letter x in common. X times x would be x squared, x minus 10 would be minus 10x. And now we have our two factors. The save only x is one answer. X equals 0 is one possible answer. And then there's this other factor, x minus 10, which in order to solve would entail moving 10 by adding. And then x would be equal to positive 10. Now again, we should check them. And I want to say one of these is going to be a dud. It'll be extraneous. If you were to put 0, the easier one, into, choose either one of these sides, if you get in trouble, this one is less complicated. 7 times 0 is 0. And that's the asymptote. So this would be undefined at the location of x equals 0. So that should be a dud. This is extraneous. Solution. 10, if you put it in there, would produce positive 70 as long as it is a positive. The argument is a y value. Right? 7 times 10 is 70, positive 70 is a y value. Therefore, it is above the x-axis. Right? That's perfectly legit. So this is the only solution in this case. 50. The log base 3 of 3x minus log base 3 of 6. I'm not happy with the style of G that I'm writing here. I can't decide for whatever reason whether it should be like that or just like that. I don't know. Driving myself crazy. Log of 77, still base 3. Okay. We're going to apply properties again to consolidate. So that once again, we could take advantage of the one-to-one property. If there is the same type of log, they're both base 3, and they're being subtracted, this applies the quotient property, which means that this log base 3 of the argument 3x would be on top and 6 would be underneath it. And this would be equal to 377. You could straighten this out, right? If you want to consolidate 3x over 6, it would reduce to x over 2. But we're solving this as part of an equation, so even if you were like me, inclined to jump the gun a little bit, we have the situation that is ideal, one log on the left, one log on the right, and now we apply the one-to-one property, which says that we just pay attention to the arguments. 3x over 6 is equal to 77. If you want to simplify this and reduce it to 2, that's fine. If you didn't do that and you moved 6 over here, you'll end up with a bigger number to start with, but the results should be the same. I'm going to try to do the smart thing. All right, I'm going to reduce this to a half, which means that this is x over 2 is equal to 77. All right, if you're solving at this point, do the opposite of division of 2, which is to multiply by 2, and then to make it legally correct, do it to both sides. 2's would cancel here. X would be equal to this number times 2, which is 14, 154. If you did it this way, times 6, you're going to get a horrible number. Let's see, 42 carried 4, 42 again, plus 4 is 46. And then you get 3x is equal to 462, divide by 3, divide by 3. 3 goes into 4 once with 1 left over. 3 goes into 16 roughly 5 times, which is 15. The difference is 1, and 3 goes into 12 4 times. Same answer. All right, so x is equal to 154. All right, here's the last one. 50. They asked you, pardon me, 52, they asked you to solve it algebraically, but then also graph it, which will be a fine point, a good problem to show that the point of intersection would in theory be the same answer. Let me do it algebraically first, and then I'll show you how to do it graphically. You're given log base 3 of x plus 3 equals 2, right? We're going to try to get it to this situation, right? Because then I can attempt to use exponential equivalence, right? Translate something logarithmic into exponential notation, the jelly bean, right? That's what I called it, right? So I'm hungry. I'm sorry. Get a little slap happy after a while. Move 3, subtract 3. Cancellation effect, we're left with just a log, which is the goal here. We want to isolate it down to just that. One of each sign says side subtract, and it ends up being a -1. Now, this is logarithmic notation, style, whatever you like. And what we're going to do is convert to exponential notation, which was from a couple of sections back. All right. Throw the jelly bean here. All right. That's the base. It will always be the base. It is 3 to the -1. All right. And you read it like this. 3 to the -1 is x. So you just have to straighten this out. If you have a negative for an exponent, that means that you're going to get a fraction realistically as an answer. So therefore, x is equal to 1/3, right? Having an exponent of 1, of course, is not going to really change the fact, right? But it would start like this as a positive, and we would just have 1/3 as an answer. X is equal to 1/3. Okay. Now bear in mind, because if you use a calculator, you're probably going to get a decimal for an answer. Remember that x equals 1/3 is really 0.3 repeating. So we'll see at the point of intersection that the x value should be 0.3333 forever and ever and ever. All right. As for how to actually do it, here's how you would do it graphically. And I hope that you will not be angry at me to go, you spelled on a period, square, do it the hard way. Again, it's good to have options. All right. I don't do this to be a jerk, I swear. All right, I want you to have the experience. The experience is really what is the most important thing. What the answer is trivial compared to that. Having some mental flexibility, which you only achieve, all right, from doing something different ways, will give you a greater, will make you a little bit more mentally sharp, and will give you a greater appreciation for the subject. Anyhow, if you have this, log 3 of x plus 3 is equal to 2, all right? If you divvy this up as this is going to be your first y value, and then that this is your second y value, you could type this into y1 in your calculator, and then superimpose it on the picture of y2, right? You probably have some expectations about what's going to happen. If you have as bare bones a linear equation as possible, that it's just y equals some number. All right, it's going to be a horizontal line. All right, this is going to be a curve of some sort, and it will be a transformation as well as it's moved from where it normally resides, right, along the axis. But they're going to intersect at some point. Right, anyhow, let's type this. Clear out of here. Go into y equals. We'll do the easy one first. If it's just 2 and you grabbed it, you would have a line that goes through 2. Okay? A horizontal line. If you're going to type in underneath it for y2, I'm doing it backwards. Call it this y2. Yeah, that's y1, here's y2, just to be consistent. I'll type in log, and again, I will attempt to get the function to show up the more eloquent way, right? Elegant, I should say. Alpha window, and you see it's choice number 5 here. Now digging. And then we have an intuitive space for the base number of 3, and a place for the argument, which is x. Use this button up here for x. X tau theta n is automatically defaulted to x. Let's change the settings. And now you have this. Plus 3. Right, so I'm going to use plus 3. And it'll be scooted over a bit, because it's a transformation technically. Okay. Now what you'll see, and you'll kind of see it in this little sort of preview here, is that they intersect. I could zoom out, but it just coincidentally is already left and zoomed in. So we're going to move the cursor to right here. There's a function that you could use to go looking specifically for the point of intersection, and I'll tell you that as an afterthought, but just to get to the answer lickety-split. If you hit trace, the cursor shows up. And I'm going to just navigate it over here to where they apparently cross, and look at what the x values are transforming into. Right? It's a little imperfect because that's just the way it is with this calculator. It's 0.3723. Probably because even though it looks like it from far away, it's really not right on the point where they're supposed to be, but it is what it's supposed to be approximately, 0.3, right? It really should be 3 repeating. If you want the more precise answer, all right, where you see satisfactory, the satisfaction of 0.3s forever, then go through these functions, right? Behind trace, there is the calc feature. You need to get to that. So you would hit second and then trace, and it would engage calc. Intersection is one of the menu options. So second, calc. Notice that choice number 5 is intersect. It's just going to ask you some sort of goofy questions. It's going to ask you, is this the first curve? And as long as we're on the logarithm and not on the line, I suppose that would be intuitive, I would go, yeah. So you hit enter, and then I'll ask you, is this the second curve, which is really referring to the line? You would go, yes, enter. And that's going to ask you, do you have any guess? Yeah, right, so you hit enter. And you notice that it spits out what it precisely is. I hate that just moving the cursor doesn't get you exactly precisely what it should be, but there is a way around that, and it is the intersection function, right? 0.333 forever and ever and ever, which is 1/3 for the x. Okay? You could do the same thing in theory for exponential equations. You can, instead of going through these methods, just graph both sides, right, and then move your cursor or get the function to tell you, right? Probably, if you do any amount of work in My Open Math, which is what we're going to be doing forthcoming, rather than the textbook, it won't give you the option, right? So, if you play ball, right, and you should, just for the sake of the mental exercise, right, be aware that you have choices, right? Ultimately, when you take a test for me, I don't care which way a person does it, one way or the other, as long as you appreciate and understand that you have options, right? So, right, that's basically it. We covered all of section 6.5 homework, all of 6.6 homework. I'm foregoing 6.7 because it's just essentially word problems for right now. And we're done with chapter 5 and 6, right? The test that again should have occurred on Thursday, which is technically tomorrow, because I'm recording on Wednesday. I can't give it to you, so at least not in person. So I'm going to give it to you as homework. Right? I'll do exactly what I normally do, which is just simply write that. All right, just to remind you. Right, for homework, all right, 1, print test number 2. This will be posted in Canvas pages. I'll try to make it an obvious thing. As a matter of fact, I'll probably post it in 2 places. I'll post it in announcements. Right. And do those problems. 2. Try all problems for homework. Right. If I collected it all right, it will probably be in the future. But I want you to do them now because I want to go over them. Right? We're going to basically go over these problems as if it was a homework, a normal homework, on Tuesday of next week. Again, I hope that I can record this in the actual classroom and then transmit like I have done today, but we'll see what the future holds. All right. Otherwise, the alternative is you're going to see me in my apartment, you know, and I'll be wearing my ugly pajamas or something, you know, and drawing on the walls like a cuckoo bird because, you know, I have a blackboard. Geez, help me, does it come to that? All right, if it does, it does. Anyhow, do test number 2, treat it like it's a homework, all right? Side note, if at this point you do not have a My Open Math account, You definitely need one. Alright? I think I have one or two people who are still lingering and don't have this account. Alright? The homeworks in the future, probably starting next week, are gonna be exclusively in this because I just cannot give you photocopies. Right? I don't have physical photocopies, and scanning them is gonna be a nuisance. I don't have a really great computer at home either. Alright? So make sure that you have this account. Okay? Thank you for coming and paying attention to me. I was happy to see you, even if it was virtually. Alright, and I hope to see you soon. Be in good health and stay safe.